Welcome to this fluid earth dynamics video entitled From Pipe Flow to Porous Medium Flow, Darcys Law. The approach that we're taking to talking about Darcys Law is to build on our previous physical and mathematical analysis of flow through a channel. And we want to do now, in that case, we examined flow, for example, magma injected in a dike, or maybe, as Chris talked about, water flowing down a river. We now want to extend this analysis to flow through a porous medium. It could be examples, could be flow of water through sand, or flow of a small amount of melt in the mantle through between the grains of a rock, of a partially molten rock. And there are basically, I think, two essential elements that we need to explore. The first one is we need to extend the analysis that we did in the previous videos where we looked at channel flow through a rectangular shaped channel, and we want to extend this now to a pipe flow, to a circular pipe of circular cross-section. And the second, we need to take into account that the fluid, when it flows through the system, it can't flow through all of the grains of the material, of the sand, for example, but it has to flow between the pores spaces in that sand. And so we have to take into account that what comes out of the system isn't coming out through a pipe, but it's coming out through small channels in a larger rock mass. And the outcome is going to be Darcys Law, and that describes the flux that comes out from the rock in terms of the pressure gradient, the driving force for making that fluid move, and the viscosity of the fluid. So previously we talked about flow between two parallel plates. An example shown here was magma being injected, for example, between two parts of the crust, and forming this famous geologic formation called chip rock in New Mexico. And we looked at the velocity gradient coming through those plates, and we saw that if we had a pressure gradient, high pressure at the bottom, low pressure at the top, that the velocity was maximum in the middle of the flow and minimum up against the plates. And we analyzed that problem in some detail. We worked out the math for that, and we end up with an equation that for the velocity in terms of position inside the channel. And again, we saw that it had a parabolic form. And we want to do now is kind of build on that kind of mathematical background and that sort of physical approach to understanding flow in a channel. And we ended up then calculating the discharge, the amount of fluid coming out, the volume of fluid coming out per unit time. We did that by calculating the mean velocity of the fluid, and then related that to the discharge by multiplying the mean velocity by the cross-sectional area. And then ultimately we calculate a flux, small q, and the flux is measuring the volume of fluid per unit time, the discharge, and then you divide that by the area. So you can think about this as the volume of fluid coming out per unit area of rock mass that it comes through per unit time. And that can be related back to the velocity. It has exactly the same units. The flux has exactly the same units as the velocity, length per unit time. Now we want to move the analysis from a channel, from a rectangular shaped channel to a circular shaped channel to a pipe. And this problem is often called a pipe flow problem. And we're going to look at flow, which again is driven by a pressure gradient. And we could look at water flowing down pipe, water coming out of the garden hose, for example, or coming out of the faucet or the bubbler if you're from Wisconsin, when you want to go to the drinking fountain. Or we could talk about flow, as in the lower left here, of magma coming up a plume or hot rock coming up a plume and forming volcanic activity at the surface of the earth. They're both pipe-shaped structures, and we want to now basically go through the same type of mathematical analysis as we did for the channel flow, but apply it to a pipe geometry. So here's the second part of the flow. So we need to first, I said we needed to get from a square channel to a circular channel. And the second part of this is we're going to look at flow through a porous medium. So we're not going to just have one big open channel, but we're going to have lots of small channels inside of a porous rock. So this is an example of water going through a porous structure in the upper left. And there's kind of a cartoon of what the rock at the grain scale might look like in the lower left. And you can see the blue arrows show you a path that the water might take. And we're going to approximate those channels through the rock as being circular cylinders And so these blue channels will get approximated to have that form. And then in the lower right-hand section of this, you see kind of a network, which is a case where you're seeing the pore structure inside the rock and the grains have been removed. So this is kind of the porous network through which the fluid's going to move. The blank spaces here, for example, there, maybe up there, or regions where there once were grains. And here are what we're going to approximate as being circular tubes. And it's a network of them kind of exiting the system. So that's the problem. We have to flow through tubes, through pipes, and we have a kind of a reduced cross section because a lot of the area is taken up by rock mass. Okay, so where were we headed? We're going to try to derive Darcy's law, or what's called Darcy's velocity. We're going to use Stokes' equation as a place to start. And we're going to look at it for a very specific pore geometry. And I'll show you that pore geometry in just a second. And what we're after is we're going to try to attain an expression for the velocity, Darcy velocity, which I've shown here. In terms of the pressure gradient, a term called the permeability, and we'll talk more about what the permeability contains in a few minutes, and then the melt viscosity. So mu in the denominator is the melt viscosity, K in the numerator is the permeability. And what we want to do is get out a form for a very special geometry. We want to get out the form of what the permeability looks like. And then you can generalize that and think about how you could do a similar calculation for different or even more complex networks of material. So the math starts here, and this is exactly what we built on last time and when we talked about channel flow. We have two equations that we want to do. The first equation describes the relationship between a gradient in the shear stress and the pressure gradient in the system, that they have to balance each other. So this was the force balance equation. And then we have a constitutive equation, which relates the shear stress to the gradient and the velocity. Okay, so that's kind of what we'd call a constitutive equation. It's for a linear material where the velocity or the gradient and the velocity relates linearly to the shear stress. And mu, again, is the viscosity of the fluid. We can combine these two. We put equation 2 into equation 1. We end up with what's often referred to as Stokes' equation that describes the pressure gradient in terms of the second derivative of the velocity. Okay, so that's where we're going to start. And we're going to use that, and we're going to generalize it in a way. You can first generalize it to 3 dimensions. We could talk about as the gradient and the pressure, and written in terms of del squared operating on a vector, the velocity vector. So when I write a tilde under a term like that, it means that that term is a vector. Okay, so that's kind of the math that we're going to deal with, but let's go back and look for a moment at the geometry that we're going to try to use to analyze this problem. So here's the structure. It's kind of what the porous medium that we're going to try to analyze will look like. It's going to be a very simplified case. If you just look at the front face of the porous medium, shown here in the lower left, it's just a series of tubes running horizontally and vertically. Then you have to imagine them running back in the 3rd dimension, so they extend back in that direction. The other tubes back all the way, and unit cells. You can think about it in terms of unit cells that compose the structure, and down in the lower right-hand corner is a unit cell, sort of like what you talked about in mineralogy. And it's just a cube with equal dimensions b on every side. So it's a series of tubes. So these are each of these red lines that I drew back here. Each of these red lines is a tube, a circular cross-section, and there's a network that looks like this unit cell in the lower right-hand corner. Okay, so let's take a look at this in terms of a tube. So here's the structure we're going to talk about. We're going to move from Cartesian coordinates to cylindrical coordinates. So rather than using x, y, and z, or x1, x2, and x3, we're going to use r, theta, and z. And the flow is going to be headed down the z direction. So the flow is coming out the tube in that direction, and then there's a spatial coordinate that tells you the distance from the center, that's the r, and a distance, another coordinate theta, which tells you where you are around the circumference of that circle. Okay, and so the velocity in principle could have a z component for flow down the tube, and it could have components in the theta and the r direction, but we're only going to worry about flow down the tube. We're not going to worry about the components theta and r. Okay, so let's go back and do some math and come up with an expression for Darcy's law. Okay, so we just said that we had a relationship that looked like the gradient in the pressure was equal to the viscosity of the rock times del squared operating on the velocity vector. Okay, and this is going to apply if the flow has to be laminar flow. It has to be, we're going to talk about a steady state flow, a flow at a steady rate. And then if we wrote this out in Cartesian coordinates, just to kind of get you into familiar territory, this would look like the partial of pressure with respect to x1 times the unit vector in the x1 direction plus partial pressure with respect to x2 times the unit vector in the x2 direction plus the partial pressure with respect to x3 times the unit vector in the 3 direction. Okay, and that would equal the bit on the right-hand side of the equation, so it's the viscosity, and then it's times these operators, the partial second derivative with respect to x1 squared plus the second derivative with respect to x2 squared plus the second derivative with respect to x3. And that's going to operate on the vector v1 x1 hat plus v2 x2 hat plus v3 x3 hat. And so that's kind of what we're trying to operate on. And now we just need to do is move that from Cartesian coordinates into polar coordinates. Okay, so we looked at the geometry and we said we're going to flow through a series of tubes, a network of tubes. And so if we're working on a tube, it's much simpler if we work in Cartesian or in polar coordinates or cylindrical coordinates rather than in Cartesian coordinates. So if we write out the pressure in cylindrical coordinates, it will look like gradient of pressure looks like the partial of pressure with respect to r times the vector in the radial direction plus 1 over r partial of pressure with respect to theta times the unit vector in the theta direction plus the partial of p with respect to z times unit vector in the z direction, right? And so all the flow, the pressure gradient in this pipe, right, is flow down the pipe. So the pressure gradient is totally in the z direction. So the only piece we need to keep is the third one. This one's going to go to 0, and the pressure gradient in the theta direction is going to go to 0. So it's just to say there's no pressure gradient along the radius from the center, say, to the wall of the tube. Okay, and then we need the second term, del squared, operating on the velocity vector. And the only term that's going to be important there is all the flow we're going to look at is going to go in the z direction, that is down the pipe, along the pipe. We're not going to worry about flow from the center of the pipe to the side or azimuthally around the diameter of or along the axis of the pipe. So that all we have to do is look at del squared of the z velocity term times the unit vector in the z direction. Okay, and we can write this out as in cylindrical coordinates, looks like 1 over r times the partial with respect to r of r, the partial of velocity in the z direction with respect to r, plus 1 over r squared, partial velocity in the z direction with respect to theta squared, plus partial squared of velocity in the z direction with respect to z times the unit vector in the z direction. Okay. So we're moving fluid down the pipe, and it's a steady flow. And so there aren't going to be any gradients in the velocity going down the pipe. It's a steady flow. It doesn't change spatially going down the pipe, and it doesn't change with the angular position theta. So the only term we have to worry about and keep in this case is this one. And so we have an expression now. The differential equation we have to solve is the derivative of the pressure with respect to position. So I'm just going to equate this piece with the piece in the pressure. So those two have to be equated. This looks like the viscosity divided by R times the derivative with respect to R of R times the derivative of the velocity with respect to R. Okay, and this is now Stokes' equation for the purpose of what we're doing now for flow down a pipe.